Hi, good afternoon, everybody. Today is August 6th in the deep summer in Taiwan, and also deep summer in Italy, Rome. And we welcome my old friend and good friend, old colleague, Professor Stefano Livi, to give a talk on his instrument, heavy ion sensors on the solar probe. But before he starts, I want to say a few words to introduce him. Stefano, I think you're a native of Florence, or are you, right? I mean,
That's correct.
wow, a native of Florence, just remember that. So therefore he did his undergraduate and also PhD at the University of Florence. But in his PhD study, he managed to spend, I think, quite a lot of time, right, at the Max Planck Institute for Aeronomy in Germany, where I worked there. That's why I met Stefano, and he then he worked in the group of Dr. Helmut Rosenbaum. And Helmut Rosenbaum, maybe not many people know him anymore today, but for us, we know he's a fantastic instrumentalist. And I think that's where Stefano learned his trick. and I think that I would say that Helmut relied on you so much, Yeah, he's a feather on the crown. And Stefano, after finishing his PhD, he stayed on at the Max Planck for you just mentioned the 20 years. And then I won't say that he fed up, he wanted to change to the environment. He went to the applied physics lab, Johns Hopkins University. I think that perhaps it's, you went to Tom Kimmich's group, right? Yeah.
Right.
And then he worked there for some, and then he moved to Southwest Research Institute in San Antonio, where his career really thrived. And can I say that? Because there he could do whatever he likes. That's what he said, whatever he wants. So he built his instrument for the solar probe and so on, and also in his ripe year, he started his teaching profession at the University of Michigan. So he's a professor there now. And so Professor Stefano Livi, please start your talk. Thank you.
Yeah. Good afternoon, everybody. Thank you, Wing, for the very kind words, and thank you very much for reminding everybody of Helmut. He has been a fantastic mentor, and I did learn a lot of tricks from him, including how to build good instruments. But let's get the talk started. And here it is. So, I'll talk today about an interesting way of tackling a very difficult problem, which is to try to understand the relationship between the atmosphere of our sun and phenomena, things that we can measure at 1 astronomical unit. And I will show you the way I do it, which is by studying the minor ions in the solar wind. And so first and foremost, I would define what are they and what effect, what property of the minor ions we can measure that they can teach us about status of the sun surface and propagation problems. Then talk about a little bit of the mission that's hosting this instrument, which is the solar orbiter mission. And then get into the core of the talk, which is to talk about the sensor itself, how it operates, and measurements that it's doing, and give you a few examples about the things that we have learned by operating that instrument meanwhile. So why minor ion sensor after all? Well, if you look at the composition of what comes to us from the sun, the so-called solar wind, you see immediately that hydrogen and helium basically make up the whole of it, 99.9% in number of the solar wind itself. And all the plasma processes that are happening are, of course, mediated by those two species. All other ions, that 0.1% of the stuff, they are just like test particles in the flow. So they don't drive, they don't control the flow, but are controlled by it. And that's the importance of them. They behave like test particles and highlight the physical phenomena that are happening there. My preferred analogy is like if you have a river that's flowing and you want to understand how the river interacts with the riverbed and the sides of the river, you can watch every single molecules and try to infer from them. But it's a lot easier to just throw leaves inside the tree and look how the global properties of the movement of those leaves, which are controlled, of course, by the river flow, but they don't control the river itself. And that's what we do. We look at the minor ions in the solar wind as test bed for the wind itself. And what informations do they carry with them? Well, first and foremost, the charge state of those ions, it's established very low in the corona. The density of the electrons and of the ions that drops like 1/r² each. That means that the interaction between electrons and ions, which is the most prominent cause of changing the charge, it's dropping like 1/r⁴, so very, very quickly. So if you measure the charge state of the ions at 1 you're measuring something that has happened within the first 2 or 3 radius of the sun. Those particles are dragged out of the solar atmosphere, most probably, but the ambipolar electric field. So the electrons are flying out very fast, and they drag with them the ions. And of course, particles that are very difficult to ionize in the very first place, they would tend to be reattracted back onto the surface of the sun. And that means that if you look at the mass of the particles and more properly the first ionization potential, that shows you how the tug of war between the gravity and the electric field, it's acting on those particles. So again, you are measuring at 1 measuring the abundance of different species as a function of their first ionization potential, phenomena that are happening in the first solar radii or thereabout above the surface. As I said before, you're looking at the stream of the river, but you're looking at the leaves and how they move. Well, the distribution functions of these ions, they are governed by the processes that are happening in the solar wind itself. Those processes are generated by protons mostly, by protons and alpha, but they are acting on every particles. And again, Coulomb collisions as well as wave-particle interactions, they change the characteristics. As I said, charged particles, the charge of the species, that tells us something. There are several processes that can change the particle charge. UV ionization, the electron impact, and to some extent, charge exchange. But the beauty of the minor ions is that they have a lot of electrons around them. And so you can have multiple ionic space. As it turns out that in space, you can only take one electron at a time. Multiple electron emission, it's a rare process. And so the ionization state will end up being a function of the density of the particles to be ionized, the density of the particles ionizing them, and a little bit of time. As the temperature of the electrons, so the energy of the electrons is changing with altitude of the sun, rising very rapidly within the first half of the solar radii above the surface and then dropping after that slowly. The available energy for ionizing the particles that changes with the altitude. And as the density drops, it will become very easy at some point to have a charge state that's established by the temperature. if you look at the probability of getting those charge changed, you realize pretty quickly that the charge of one ions, take here, for example, magnesium, it's a hint about A, what was the temperature of the electrons when the particle were ionized, and B, from the percentage of each charge state, where that has been. Like, for example, at 2 solar radii, the things have already been established, and you find out that magnesium has by 80% or 85% is charge state of 10. There is a bit of magnesium, which is charge state of 9, but very little percent or thereabout below. And electrons have not reached an energy that was able to change the charge state 10 into charge state 11. And that measuring the charge state will give you a hint about the process that had been acting. In the solar corona, with the temperature over there in the 1 to 2 million degrees, the equilibrium is such that basically helium is totally ionized, protons are totally ionized by the case. Helium has charge state of 2, totally ionized. Carbon and oxygen have almost reached the fully split charge state, and iron can hover in the 10 to 12 charge state. But the important point is that measured at 1 AU, that charge state gives you a hint about A, what the temperature of the electrons has been, the history of those particles themselves. But not only that, there is some more that you can do. Particles that have a larger cross-section for electron impact ionization will freeze at larger solar distance. They have more time. Even 1 over r to the 4th power still means. And so by looking at different charge state of different ions, here is, for example, from Ellie in 1997, a comparison of charge state of oxygen and charge state of iron, that's telling what the electron temperature would have been from the sun itself. I care a lot about trying to convince people not to use the solar wind velocity as a permanent marker about what the solar emission process would have been. And the reason is very, very, very simple. If different regions of the sun emit particles with different velocity, then particles that are fast, they will tend to catch up with particles that are slow, and particles that are slow will tend to lag behind particles that are fast, which naturally brings a curve like the red one depicted here, which is a superposition of 10 solar radiations. And you see that if you try to identify the emission regions based solely on velocity of the wind, you get somewhat undetermined characteristic. But instead, if you look at the minor ions informations, like, for example, the temperature of the emission point as derived by the oxygen ratio, or the magnesium to oxygen. Magnesium, it's easy to ionize. Oxygen is a little more difficult to ionize. You see that the boundaries are determined in a much sharper fashion than you would otherwise. So looking at the solar wind velocity, it's a first hint. But if you look at the composition and the charge state, it's a much better hint about where particles would have been coming from itself. And talking about processes, it turns out that most of the minor ions, they write faster than the protons themselves. In the fast solar wind, this difference is more pronounced than in the solar wind itself. Like, for example, if you look at the velocity of oxygen as a function of the velocity of hydrogen, and the dashed line there, it's the one-to-one relationship. You see that at slow velocity, they tend to be rather very similar, but as the velocity of the hydrogen increases, then the velocity of the oxygen tend to increase more than that. Same observation can be done with the temperature of the different ions. For slow solar wind, typically the temperature is equalized between protons and the heavy ions themselves. That solid curve there, the dotted curve there. While for solar wind that's a little higher velocity, the temperature tend to be proportional to the mass itself. Equal temperature means things are dominated by collisions. Equal thermal velocity, so temperature proportional to the mass itself, it's a hint that there is a process that tend to wave dominate the solar wind itself. And again, looking at the easiness of ionization of the particles, you see that particles that are difficult to ionize or more difficult to ionize, like noble gases or oxygen itself, they have a composition that is pretty much what you expect from the solar system itself. While particles that are easy to ionize, like sodium, calcium, or magnesium, they tend to have an overabundance with respect to the solar itself, and the difference can be large. Can be difference between twice as much or 3 times as much. And it's very clear if you look at the color of each dot that things are organized from where the particles are coming from. Again, simplistically, I hate that, but it's things that everybody understands. Slow solar wind, which tends to come from interstream, will have an overabundance of particles that are easy to ionize, while fast solar wind, or solar wind that's coming from coronal holes, tends to have a percentage that's pretty much the same as the sun, meaning that particles, when they try to get out of the sun, if they're easy to ionize, they will fly out rather soon away and get there as well. So, why is that? Well, it's difficult to do that because the informations that we had up to today were using different instruments, different calibration, different regimes, and we're getting different results from different experiments. And I hope to get a glimpse of that by using the solar orbiter itself. Going a little bit higher in energy than the typical solar wind energies, which are in the keV range. If you go in the MeV range instead, you see that there the isotopic variations are even more pronounced than regular solar wind. You get variations by about 4 orders of magnitude of the helium-3 to helium-4 ratio, for example. And why is that? It's still a matter of research and debate. Is it easy to make all these measurements? Well, not really, because as things move away from the sun, if you look at, for example, variation related to solar flares, or solar explosion on the surface of the sun, tend to disappear as you move along the away from the sun itself. The left, it's a plot of the protons as they were measured by Helios 1 at 0.3 AU, and the same event observed at 1 AU. And you see, while Helios shows clearly 5 events related to shocks that were happening on the surface of the sun, this knowledge, by the time that we reach IMPAID, it's completely washed out. What do we want to learn out of that? Well, if you look at the particles that are not in the plasma regimes, part dominated by either wave interactions or collisions. Anymore, or not even close to Maxwellian, it's a power law tail. And those ions carry interesting information, in particular because these particles are thought to be the seed population for energetic particles, for acceleration around the particles. And one striking observation is that the chemical composition, so the mass ranges of the suprathermal particles and of the energetic particles, is different than the chemical composition of the solar wind itself, which is again different from the chemical composition of the surface of the sun, the body of the sun itself. Why is that? Well, one easy way to start getting a grip on the processes is to look at the particles that are not energetic and not thermal, but the particles that are in between. If the composition is different, at what point does it become different, and related to what processes that then? And again, last theory element for today is that if you look at things that are happening on the surface of the sun, together with things that have been measured at 1AU, you get the idea about where in the sun, where the interplanetary space, the coronal mass ejections, the interplanetary coronal mass ejections are accelerated, and where they come from. So this is to give you an idea of why we do that. And let's next talk about the solar orbiter mission itself. It's the very first conference I attended was a conference that was planning to go as close to the sun as it was feasible. It was called at that time Fire and Ice, and that morphed into some other things. But eventually, we made into making that into a mission. And the solar orbiter mission is important because, first of all, it spans all the distances between 0.3 and 1AU, and they hope to overcome that acceleration as mirroring that I showed you about. But also, the planning of the mission was to use the gravity assist from Venus to cramp the orbit out of the ecliptic so that we could have a glimpse on the north and south pole of the sun, so the polar regions of the sun, to see what visually it's happening there. We have measured the particle characteristics with Ulysses mission, but Ulysses did not have any optical measuring capabilities. And so by complementing measurements done with optical instruments on the surface of the sun, particularly the poles and the oscillations on the poles, with events that you can measure at 0.3 AU, so very close to the sun, we are hoping to close that bridge. Again, has been launched in 2020 from Cape Canaveral, and every time that encounters Venus, then we crank up the orbit so that eventually we get up to 30 degrees over, and that's in the extended mission of the sun. Why is solar orbiter so special? First of all, it's the first spacecraft that went inside the orbit of Mercury. After solar orbiter, there will be solar probe that went even closer in. But solar probe, it's a much simpler mission in that it does not have optical instrument. There's a coronagraph that's measuring the flow of the particles, but no direct measurements of the surface of the sun. So the remote sensing, its capabilities is what makes solar orbiter very, very special. One other thing is that if you see solar wind and you see things changing in the solar wind, if you are at 1AU, you cannot tell whether the changes that you have seen are due to changes in time. Something has changed in the surface of the sun that has produced a change you're observing. Or since you're traveling with respect to the sun, you're traveling from one region to the next one, and the changes that you're seeing are related to spatial changing. Orbiter will allow to go and stay almost stationary on the surface of the sun. As to that point, we are sure that what we see, if there's a change, is a change related to something that has changed on the sun itself. And my instrument is part of a suite of instruments. It's called the SolarWind on the 4 pi stereodian surface in the energy typical of the SolarWind electron energy. The proton and alpha sensor, which measures proton and alphas, as the name says, up to 20 keV. And my instrument, which is the heavy ion sensor, which measures from 0.5 to actually 75 eV. And all these sensors are served by a common DPU, which is 2 redundant element. Okay, so now we have defined what's the science we want to do, and we have defined the importance of that science and how to do that. And what do we need to measure to understand the heavy ions? Well, you want to measure the mass, as to look at this tug-of-war competition between gravity and electric field. You want to measure the charge, because that's a direct measurement of the temperature of the electrons in the corona. By measuring different ions, you measure temperature at different heights. And you want to look at the 3D velocity distribution, so you have to measure 5 quantities for each particle that's arriving. And we do that by making 5 direct measurements: the directions of arrival, which one is measured by electrostatic deflection, one is measured by using separate anodes. Then the energy per charge of the ions by means of an electrostatic analyzer filter. And then we measure the speed of these ions by measuring the time of flight into a given cell. And then at the end of the cell, there is a solid-state detector that measures the total energy of the ions. And that's the core of the instrument. It's not a new instrument. It has been flown before on Ulysses, it was called SwRI, as well on ACE. But this is a last incarnation of the instrument. But the principle of operation is pretty much the same. You use angular deflection to basically identify the direction in the sky the particles are coming from. Then you have an energy per charge analyzer that selects only a sliver, 10% or thereabout of the energy per charge of the ions that's coming in. Then we use a post-acceleration, in his case is 25 kilovolt, to enhance the properties of the ions so they can measure better. And then we have a time-of-flight telescope that's kept at high voltage, where we measure the time of flight of the ions by means of microchamber plates. And at the end, there is a solid-state telescope, solid-state detector telescope that measures the total energy of the ions. That's a cut through the instrument that shows how the things are stacked up together. And these are the characteristics of the instrument. Notably, geometric factor is tuned to heavy ions. It's in the 10 to the minus 5, 10 to the minus 4 square centimeter and steradian type geometric factor, with a resolution that's sufficient to determine ions from each other, and an angle that covers the SwRI itself. And here's a model of the experiment. Particles are coming in the sensor itself, and the emit electrons from the top. These electrons are collected time of flight wise via the microchamber plate, and particles then keep on going for about 9 centimeters and hit the solid-state detector, releasing electrons, the green ones. They get the stop signal itself. And this is a typical spectra in energy per charge versus time of flight space. that shows how particles are divided. And coming from the left, you see the proton particles. Then next to them, the alpha particles. And next is the oxygen, the three main blobs. The longer one, it's helium, singly ionized. It's long because it's a pickup ions. We'll talk about them then later on. And then there's a group of the ions. Okay, so we know what we want to do. We know how to do it, the sensor. And let's look a little bit about what we have learned out of this sensor during the 4 years that has been flying around. First, let me talk about the suprathermals. If you remember the science section, suprathermals are those whose energy it's in between the classical plasma energy and the energetic particles energy, so between the keV and the MeV. And I'll focus on the 5 to 70 keV range. Why do we do that? Well, again, the chemical composition of the plasma is different than the chemical composition of the energetic particles. Not only that, but up to today, we were just confused by hovering at 1 AU by the propagation, scattering that's happening to the particles. And whenever a shock passes by, then we know that there is a big change in properties. If you look at the top panel on the right, which is just an energy per charge versus time, at the time of arrival of a shock, of course, the mean velocity of the particle rises. That's the effect, the acceleration produced by the shock itself. But if you look at the chemical composition, you notice that also after the shock, you have a much more rich in composition type of particles. And let's look at the particular shock, the one that happened on Halloween of 2021. You see that here's plotted in green the velocity of the particles, green and red, and this plotted here, it's the helium velocity. And you see that at the time of the shock, between region 1 and 2, the velocity changes from 300 about into 450 kilometers per second. It's not particularly fast solar wind, but it's a notable change. It was a strong shock. And what we see right after the shock has passed is that you not only have the typical solar wind composition that we saw before, but all of a sudden you get a lot of particles in the energy per charge regime of 5 to 70 keV that were not there before. Oops, just went backwards. And what I notice is that the energization of these particles on that particular shock was different for different species. Well, collected here are spectra, so energy per charge spectra of protons in the top left, alpha particles in the top right, and single ionized helium on the bottom left and oxygen on the bottom right. And you immediately notice that there is a striking feature. The protons and the helium do get accelerated particles in large quantity, while the alpha particles and the oxygen, they get a little bit, if any. Certainly not the order of magnitude more intensity that the protons and the helium would gain. And why is that? Well, it just happened that in May of 22, we were lucky enough to get 2 shocks happening one after the other. And if 2 shocks happen one after the other, then at the end, the energization appears to be similar for all particles involved. And what it's telling me is that the ionization happens preferably on particles that have already some velocity relative to the main population itself. Those particles, those suprathermal particles, they are the ones that pick up the energy fast. And that's start explaining the difference that we see in the composition of the energetic particle versus composition of the plasma itself. It's because processes like shock tend to accelerate particles that have already there, more preferably with respect particles that are just plasma driven. So looking at minor ions has given us for the first time a proof that these suprathermal particles are important in the process of the energization of the solar wind itself. The second argument I want to talk about is something that has been very interesting to examine, the pickup ions itself. Pickup ions are produced when neutrals all of a sudden change their charge state. If they change their charge state and they are embedded in a flowing solar wind, then there is an acceleration process that acts on those particles. They are picked up by the electric field or by the magnetic field that's moving with the solar wind. And it's the B cross B field that's accelerating those particles around. Once they're accelerated, they are convected together with the solar wind itself and form at first a ring distribution around the magnetic field, and this ring distribution gets very quickly scattered around to form a shell distribution. So when you measure these pickup ions at some distance from the sun, some distance from the ionization moment, you find a distribution that's basically flat between a fraction of the solar wind speed up to 2 solar wind speeds, but then after that it ceases. It's because the acceleration process can only bring particles up to twice the solar wind speed. Where are these particles coming from? Well, they are neutrals. They can come from anywhere, but the 4 more common sources that are known are, first of all, the interstellar neutrals. At 1 AU, carbon and neon are the, helium and neon are the 2 most common elements. Hydrogen, carbon, and oxygen, which would have been more abundant in the interstellar matter, they are ionized by the solar wind radiation and pushed away from the solar wind pressure at the distance of about 5 AU, so don't see much of them. But down to 1 AU, you see the helium and neon itself. And then comets, they release neutral gas, which eventually can get ionized by the solar radiation or electron impact from the solar wind that get picked up. And in the close proximity of planets and moons, you have ions from there. But there was another source that we were not able to identify, which was the inner source itself. Why an inner source? Well, as I said, carbon, oxygen, and protons, they cannot propagate much inside 1 AU. Yeah, hydrogen still has a 10% probability of getting there, but it's very little. And oxygen and carbon basically have no possibility of getting inside 1 AU, but you measure them. So they must come from somewhere else. And here's the measurement of the of those particles made by George in 2000. You see that even at 1 AU, classically, you see quite an important part. Where are they coming from? What is the source of them? There's been several models proposed, some better, but without having the data that enables to measure directly the composition, it was difficult to try to understand. And what we have been working on is to measure the energy per charge distribution of those ions, which is possible by using his instrument. And what you see is that helium plus it's behaving rather differently than carbon and oxygen, essentially at all distances from the sun. He has plotted a series of measurements from 1 AU to 0.3 AU. And you see that while the carbon and oxygen do not change dramatically between 1 AU and 0.3 AU, the helium certainly does. And the closer you get to the sun, the more you see a low energy component of helium in the 1 keV range, or the 1 solar wind velocity range. Not only that, but while the helium plus shows the typical characteristical drop at twice the solar wind velocity with intensity in energy per charge, the carbon and oxygen don't seem to look at that. And our interpretation is that the helium plus has two components. One that is coming from the interstellar space, which is the one that shows the classical pickup ion drop at twice the solar wind velocity, while the carbon and oxygen, as well as the low energy component of the helium plus, they are generated by interaction of the solar wind itself with dust that's present in the range from 0 to 1 AU itself. And the reason we think about that is that if it's a pickup process, then it has to have a distribution that drops like this. While those particles, they don't show anything that kind. They more resemble the original solar wind velocity, hinting that these particles are simply solar wind origin that get modified in charge by interaction with grains and proceed their way that way. Talking about pickup ions, we were lucky with SwRI to fly first through the Venus atmosphere. And this is a plot of the trajectory of the solar orbiter through the Venus. And unfortunately, we could get measurements only in the green area, meaning that as soon as we passed or came very close to the shock, theoretical shock of the Venus bow shock, then we did not measure. But still, we were able to see a population of particles, which is, if you see my mouse in this area, if you don't see my mouse at the particles, they are oriented along the oxygen expected track. And these pickup ions from Venus are characterized by coming into bursts, not a continuous process, but very, 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 very sharp. So within our capability of time measuring, which is about 30 seconds, particles were changing 1 or 2 orders of magnitude in intensity. And my personal interpretation is that since they are coming at this type of burst, it's not a continuous leaking from the shock, but it's basically temporary, limited leaking from a shock, which would happen when you have reconnections happening at the shock fronts itself. And also, we were lucky to cross the comet of a tail, as I put it, to catch the comet by its tail in December of 2021. And this is a typical energy per charge versus time of flight spectrum that we collect. And this is what we are getting by coming through the tail of the comet. As you see, all of a sudden you get a number of single ionized, double ionized ions that were definitely not there before. And These are varying with time. This is a time plot of 3 days, 4 days, one after the other. You see that there is a maximum, and this is the spectra of the particles we have collected, showing that there is a quite contribution from single ionized oxygen, which is not constant. Again, is varying a lot, and single ionized carbon. So my 45 minutes are finished. Let me offer you some summary and conclusions. It's important to measure the minor ions because they carry with them information about what were the conditions at the moment that they left the sun, and how that has influenced themselves. Their chemical composition is important for both solar-related processes. We want to know how these particles get out to the sun, and looking at the Fippe effect gives you a handle on that. But also to try to understand what are the processes that accelerate particles at or around shocks themselves. The HIS instrument has been lucky enough to fly on the right spacecraft. That brings you all the way down to 0.3 AU, avoiding this mirroring effect, but also has been designed as to have the necessary resolution and sensitivity to address a bunch of very important science questions. And the solar orbiter mission mentions all it. Well, thank you very much for your attention and for your patience in listening to me.
Okay, thank you, Professor Livi, for such an engaging talk. So now it's the time for the Q&A section. Does anyone have any question? And please feel free to turn on your microphone and ask to Professor Livi. So here I see a question from Wendy.
Hi, Stefano.
Hey, Wendy.
It's really nice work. And so I just have one quick question. And so I'm not sure. I know you mentioned the interaction with the interstellar grains, but I don't get a full understanding of the interaction with the grains, the dust grains.
Well, you're not alone. It took us the better part of 20 years to focus onto that problem. The inner source was discovered by George and co-workers already by measuring these wicks, and just couldn't figure it out. And what we think is happening, it's what's on the top right part of this figure. If the grain it's small, it will present itself as more cross-section for those particles to come through. So it works like pretty much the carbon foil into the carbon foil experiments. Particles come in, and when they get through the system, the carbon foil or dust grain, they come out with a charge that is different than the charge that they had before. So think about having neutral carbon that's or oxygen that's coming through from the sun and interacts with one of these grains. After the interaction, as shown was shown by Frederick in the bottom right part of the figure, this carbon will come out with a charge that is different than the charge that the ion had before, and can have there's a certain probability, like 10%, that the carbon come off with either charge plus or minus out of that. But the important point is that this carbon will not change its original velocity. So the solar wind carbon that was coming and hitting these grains effectively come off still charge positive and still having a distribution that's the one we originally have. But it's all the carbon that came in as a neutral that get morphed into a positive charge that will enhance the intensity of the carbon over and above what was coming in. So essentially, it's a charge exchange process that's happening on the surface of the grain that changes the charge, and the outcome is charge 1, 10% of it, but does not change the velocity. That's why you find distributions which are resembling the original solar wind distribution for those ions, because that was the velocity they had before. But instead of having charge 6, or 4 or 6 for carbon, or 6 or 7 for oxygen, that they had in the original solar wind, their charge out, it's 1, as prescribed by the interaction with the dust itself.
Thank you.
I could go on forever on this. But you know, 45 minutes is 45 minutes.
Yeah, I miss my time in San Antonio.
We miss you too. We miss you too.
Yes.
At some point, we have to talk about the other baby.
Oh yes, but baby Campo.
Yeah.
The Strofield. Yes. Yes. Okay, thank you. And I also have to run for another meeting. So really hope to see you soon in some other conference. Yes.
Yeah, maybe at AOGS next time.
Yeah, yes. But I saw your name this year, but you didn't show up.
No, I was in Japan that particular week. Yeah.
Okay. Okay. Bye.
Bye, Wendy.
Thank you.
So, any other question? Yeah, I have one question just for the curious. I'm Ren Kai. I'm Ren Kai from TSU. So you have mentioned that the solar orbits will gradually adjust its inclination to observe the sun's polar region. So what are the expected scientific findings from observing the sun's polar regions?
Okay. Oh, great question. Let me be frank. From the solar wind perspective itself, not much. And the reason is that we have already flown a particle instrument, a particle mission called Ulysses, over the poles of the sun for several rotations. So we have already made the major discoveries. But what's new, and what will be new, it's the optical measurements that we will be able to do with the instrumentation on board the solar orbiter, which for the very, very first time, we look at the sun over the poles. We do not know what to expect there because it's never been measured. And one thing that we are eagerly waiting for is to look at the helioseismology results from the optical instrument, because the poles of the sun are where we suppose that the circulation that's running underneath the surface of the sun, it's reclosing. And that will tell us essentially the origin of the magnetic field of the sun. Without that measurements, it will be very difficult. Well, it's been very difficult in the past 30 years or so to get a closure about what processes are generating the magnetic field and what currents are generating the magnetic field. So for the particle perspective, we are not at the forefront, but it's the optical measurement perspective that will break new ground.
Okay. Okay, thank you. I'm looking forward to seeing the relative finding. And so here I see another question from the Dr. Ian Lai. So he says, thanks for the nice talk. As the solar orbit moved to high latitude in its solar orbit, what change do you expect to observe in the measurement of heavy ions?
Good question too. When you are in the ecliptic, you are hovering into the interstream type of region, coronal hole region, which is characterized by
Okay, thanks for Professor Livi's so detailed answering. So is that answer your question, Dr. Ian Lai? Okay, I see. So any other questions? If no more question, I think it's about the time. So let's once again thanks Professor Livis for today's talk. And we have other online talk on August 27. So please visit our TSU website for more information. So thanks you all for joining us today, and thanks Professor Livis again. And I hope you enjoy your journey in Italy. So, so we will see you next time. Thank you.
Okay, thank you.
Thank you. Bye bye. Thank you.